Yes, student. Let us discuss now the syllabus from the paper 2, the diborane about which we were discussing. I like to know from you, could you able to read this content
Yes,
which is
sir.
on the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Very good, very good, very good. So let us begin our today's discussion with the applications or importance of the diborane. First application, diborane is used as rocket propellant. Means it's a fuel which is highly exothermic, or where reactions remain very highly exothermic, and accordingly the energy that the rocket will be get. So for the propellancy of rocket, fuel is necessary. Instead of saying fuel, we say a proper scientific word as a propellant. Diborane is used as propellant. Second application, it is used for manufacture of borophosphosilicates. Means is a form of glasses, and their diborane is used. Third one, in most chemical reactions, it is used as reducing agent. Maybe its compounds also are used as what the reducing agent. The fourth one, diborane is used as catalyst and or rubber vulcanizer in the polymerization reaction. Catalyst during rubber vulcanizer and in polymerization reaction. Means as a catalyst it is used. Next one, it is used as a doping agent in the manufacture of semiconductor devices. Actually, for semiconductivity during doping, we need electron deficient element. Silicon is tetravalent, germanium is tetravalent. But in that, suppose if we add impurity which is trivalent, boron is trivalent. Boron has 3 electrons in its outermost orbitals, but not 4. So general skeleton remains of silicon where 4 electrons are there. Tetrahedral arrangement is there. But in that tetrahedral network, if we add impurity, say the boron, then 1 electron will be less relative to the other. I want answer from you, student. If there is a 1 electron less or few electrons less compared to the expectation, then that kind of doping, that kind of impurity addition is called as which kind of impurity it is? Positive or negative? Yes, waiting for your replies. You can unmute and talk.
Repeat, sir.
Okay, see, silicon and germanium are semiconductors, and semiconductivity can be influenced by means of 2 ways. One, by heating, by increasing temperature. If you increase temperature, the electron which are at low energy level will go to the high energy level, and those can be freely movable, and because of that conductivity can increase. So this is the first way, that's called intrinsic semiconductivity. Other, we can do such a thing in that material or element that electron movement will become free. If electron movement becomes easy, electron moves freely, then conductivity adds, conductivity increases. So we can increase that conductivity by means of adding impurities. That is called as doping. My question is, if we use boron as an element for doping, which is trivalent, then such kind of doping is called dash kind of, that's a semiconductivity.
P-type.
Yes, exactly. Prathamesh is right. It is a P-type doping, P-type semiconductivity. So their boron is necessary. But this boron we are getting from whom? B2H6. Therefore, we are saying B2H6 is used for manufacturing of the impure semiconductors or for the extrinsic semiconductivity. This diborane is used as a doping agent. Okay, these are the few applications that is expected from you as a notes. First point is applications of the diborane that you need to write. About structure of diborane, already I had a discussion. Now let us come to the next borane. That's a tetraborane. Its formula is B4H10, and structure is very interesting. Total 4 borons are there. How are those 4 borons? See, 1 boron below this square for consideration of 1 plane, and 2 borons are there in that plane. 1 boron is upside. Labeling to the boron, how is done? First 2 borons are in a plane, are along the side of the square. 3rd boron is upside and 4th boron is downside. As in case of diborane, terminal hydrogens are there. Here also terminal hydrogens are there. To boron number 1, there is only 1 terminal hydrogen. To boron number 2, there is a one terminal hydrogen. To boron number 3, two terminal hydrogens. Boron number 4, two terminal hydrogens. I hope you are getting this point. Terminal hydrogens means what? Means the hydrogens which are attached to only boron. Those are terminally linked. Bonding will end. If I move from boron, if I come to hydrogen, afterwards I will not find the bonding. There is no any kind of bridging. Such terminal hydrogens are there. So total, how many terminal hydrogens are there? Here for boron 1 and 2, each boron carries one hydrogen, and upper and lower boron, boron 3 and boron 4 carries two terminal hydrogens. So total, how many terminal hydrogens are there? 6. So 6 terminal hydrogens. And what's the kind of bonding it is? Two centered, two electron, two nuclei, two atoms, two electrons do exist in that bonding. One electron from boron, other electron from hydrogen. That's a two centered, two electron regular bonding. If I have to talk about the bridged bonding, bridged hydrogens, see how bridged hydrogens are there. Boron number 1 bridges with boron number 3. Boron number 1 bridges with boron number 4 via or through hydrogen. So here one bridge, boron 1 and 4 bridge, boron 1 and 3 bridge. There is no direct linkage between borons. They are linked through hydrogen. Similarly, boron 2 is linked to boron 3. That's a bridged bonding. Boron 2 is linked to boron 4. That's a linked bridged bonding. So what are you understanding? Whoever central borons are there, boron 1 and boron 2, those are bridging to upside boron and downside boron. Each boron, is boron 1 and boron 2, is showing bridged bonding to lower and upper boron. So in total, how many bridged bonds are there? This boron 1 and boron 3 through hydrogen is the first bond. Boron 1 and boron 4 through hydrogen, second bridged bond. Boron 2 and boron 3 through hydrogen, bridged bond. That's a third bridged bond. Boron 2 and boron 4 through hydrogen, it is a fourth bridged hydrogen bond. So total 4 bridging bonds are there, 4 bridges are there. BHB is a name for those bridges. And what is the category of that bonding? How many centers are there and how many electrons are there? In each bridge, you will find 3 centers. One boron means 3 nuclei are there, 3 atoms are there, one hydrogen and other boron. But electrons are only 2, as is the case for the diborane. If this boron contributes, then in this bridge, other boron will not contribute. But for other bridge, this boron will contribute and here will not be. So likewise, there is a linkage between that. Means if I had to talk about this boron number 2, if boron number 2 is contributing for upper bridge, then for lower bridge with boron number 4, it will not contribute. If boron number 1 contributes for lower bridge, then for upper bridge, it will not contribute. Boron number 3 will contribute. So there's a mutual understanding among them. So total, how many such bridged bonds are there? 4. What's the type of that bonding? 3 centered, 2 electron. 3 atoms are there, but electrons are 2. That's a banana kind of bonding. That's an electron deficient bonding. And that's the importance, or it is a essence of this boranes who are electron deficient. Diborane means B2H6, about which we discuss, and here other borane, that's a B4H10. It is called as tetraborane, that we are discussing. Its bonding we are discussing. In addition to the terminal and the bridged bonding, there is direct bond between boron and boron. Actually 4 borons are there, but out of those 4, only 2 borons are attached to each other, linked to each other. Being boron a metal, a metallic bond do exist. Metallic bond in the sense what? But sharing is what considered there. Here boron 1 has 1 electron, boron 2 has other electron. So there is a linkage between boron and boron. So this boron 1 and boron 2 bonding is a 2-centered 2-electron bonding. Boron 1 and boron 3 through hydrogen is a 3-centered 2-electron bonding. Boron 1 and terminal hydrogen is a 2-centered 2-electron bonding. Why for we should discuss this 2-centered 2-electron, 3-centered 2-electron likewise? In order to calculate total number of electrons involved in the bonding. You can work on that and you will find how many electrons are involved in these all bondings. Means if I talk about this terminal bonding, 2 electrons are involved. If I talk about this bridged bonding, there are also two electrons involved, but centers are what? Three. But from whom to consider electron and from whom not to consider, that's a wisely you have to choose. And total you have to calculate how many electrons are involved in the bonding. Yes, can anybody answer total how many electrons are involved in the bonding? I told here. How many bonds are there? Bridged bonds? Four are there. How many direct boron-boron bonds are there? One. How many terminal bonds are there? Six. Total how many electrons are involved in a bonding during this before H10 formation, tetraborane formation? Here hint is given to you. Here each bond means three center two electron, means each bond is resembling for two electron. Each bond means resembling for two electron. Each bond is related to two electron. Hint is there. I want answer from you. Total how many electrons will be involved in this bonding of before H10?
6 electrons.
How many?
22.
Prathamesh is saying 22. What is the answer of others? Before that, I got one answer. Okay, I help you to give the answer. Total, how many bonds are there? What types of bonds? Three types of bonds are in front of you. On screen, three types of bonds are there. One bridged bond, other direct bond, and terminal bond. There are types of bonds. Total, how many bonds are there? That's my question.
11.
11.
Yeah, one answer. Very good. 4 plus 1 plus 6, 11. And in each bond, how many electrons are involved? 2 electrons. So it's a game of 22 electrons. Okay, I hope you got this point. Simple question it was. Only you have to apply the logic, applications. You have to train your brain for that. Okay, see here now. Boron hydrogen terminal bond length is 1.19. Here it is expressed in angstrom in it, but a new train is we express such bond lengths in nanometer. Means meter in the metric system is a proper unit. So in terms of meter, nanometer, picometer, these are the units by which we can express such small distance. Here 1.19 angstrom unit is a terminal bond. But if we talk about the bridged, the bond length is 1.43. It means terminal hydrogen is tightly bonded and it is loosely bonded. Here two centers, two electrons. Centers and electrons are same. Here centers are more, electrons are less. Electrons are the joiner. Electrons are going to link. Electrons are going to mingle. Electrons are going to overlap. So this bond length you are finding is larger. You think about see boron 1, boron 2 distance. It is 1.71. While boron 2 and boron 4 distance is 1.84. Means boron 1 and 2 are closer. They are closer because there is a direct bonding between them and therefore they are closer. While this boron 2 and boron 4, there is a no direct bonding. You are finding dot here. This is not a bond. It is only to inform this bond length that bond was constructed. It is shown as if like there is a linkage. It is not linkage, actually to show the length this dot lines are used. It indicates boron 1 and 2 only are linked to each other, two centered electron bond, while boron 3 and boron 2 or boron 2 and boron 4, there is a no linkage between them. That's a direct linkage. Indirect linkage is there. So on the basis of bond length, we can describe the efficiency or strength of the bonds. Yes, students, are you getting this point, what I'm saying?
Yes, sir.
Yes.
So you can go through this PDF file and you will find the calculation that how total number of electrons are what calculated. What the Prathamesh said, no, it's a simple one, 22. Total number of bonds into 2. If you do, then you will find that. But overall, how many electrons involved, those are discussed. Okay. Next point is one new compound, that's a borax. So before that, is the structure of before H10 clear to you? If you want other kind of imagination, then I will show that also. If this structure is clear, well and good, I move to the next point. Do you want to see the other format of structure? Okay, just wait. Let me take the help of the Google. Okay, I share this screen now. Could you able to see the various structures?
Yes, sir.
Yes, sir.
Different ways are there. It's a three-dimensional model. Here, simple ways sketch is given there. These two borons are attached, while other borons are linked by means of bridged hydrogen bonding. And here, where there is no direct linkage, those two borons have the terminal hydrogens. It's one of the simplest diagram. If you want to see this diagram, also is a simple one. Yes, could you able to see this diagram? Is it possible to read this diagram, or is it a small one? Shall I magnify that?
Visible.
Okay, could you read that diagram now? Okay, magnified. See here, it looks like a somewhat systematic, but understanding is important. this boron and this boron is linked by means of bridge bond. Here there is a no bond. This is a mistake in this diagram, but it was looking like a good proper, but here there is no bond. Only through the bridge it is linking. The two borons are directly attached. Wherever such bridges are shown and triangle you are finding, base for that triangle is not there. Other things are proper in this diagram. Here terminal hydrogens are there. Bridged hydrogen, terminal hydrogen, bridged hydrogen, terminal hydrogen, terminal hydrogen, bridged hydrogen, terminal hydrogen, and terminal hydrogen. So this is other way of representation of that diagram. Here further correct diagram. Okay, this is a three-dimensional imagination. A good imagination is there. Yes. Here you can find these four borons. These structures are actually tetrahedral. sp3 hybridization that each boron undergoes. I want to know from you. Could you able to pay attention to this diagram?
Yes, sir.
Is it readable, understandable?
Yes. Yes.
Okay, good. Okay, see here boron number 1 and boron number 2, direct bonding between them is there by red color. That bonding is represented. Boron number 3, let me consider it, is left side, and boron number 4 to right side. Boron number 3 and boron number 1 linked by means of bridged bond. Boron number 3 and boron number 2 linked by means of bridged bond, bridged hydrogen bonding. Boron number 2 and boron number 4 linked by means of the hydrogen bond. Boron number 4 and boron number 1 bridged bond, bridged hydrogen bond. And here on boron number 3, 2 terminal hydrogens are there. Boron number 4, 2 terminal hydrogens are there. And on each boron which are directly linked, that's the boron number 1 and boron number 2, terminal hydrogens are there. See, those terminal hydrogens are pointing downwards. This also going downwards, not exactly downwards, but in the direction. Of course, it's a tetrahedral arrangement, no? So it's a, in true sense, a structure is. Means if I cut this tetraborane molecule through this boron and this hydrogens, then this hydrogen will find mirror image here. This hydrogen will find mirror image here. This hydrogen also will find mirror image. This hydrogen also will find mirror image. Such symmetry is there. Plane of symmetry do exist. So other many symmetry operations we can try on this before acetal molecule. So in future, this symmetry operations will work, but for the structure should be clear. So is the structure of tetraborane perfectly clear to you?
Yes, sir.
Yes, sir.
Yes.
Yeah. That screen was shared, no, at that time. That three-dimensional image was there, no? You could see that three-dimensional boron, red
Yes,
or
sir.
pink color bond. Okay. Because
Yes, sir.
okay.
Yes, sir.
Now I share the presentation. It's a borax, a new compound. And while studying compound, a preparation properties are to what study here. So how to prepare that borax? Borax bed test. Have you performed charcoal test at 11th or 12th standard in semi-micro qualitative analysis? Charcoal test.
Yes, sir.
You have to pierce a charcoal and you have to put that the salt, and then you have to heat that by reducing flame, or you have to blow, as like goldsmith blows the flame, because you have to blow the flame, you have to heat that, you have to reduce that, reducing flame you have to use, and what the color change you find accordingly in inference you are getting. And in that additional point was there borax bed test. So we have to add the borax there, and then the same test we have to perform. That's a charcoal test we have to perform. And that borax bed test was giving a significant results. That was very helpful to find out the basic radicals, means metal. So that borax is one compound. Means if you heat that, it becomes glassy, somewhat transparent. Otherwise, it is like a powder. Carom powder, as like it remains over there, it is like a powder. Now, last year we have not conducted any experiment, therefore you don't know. But this one experiment was there where, with the help of borax, you are performing titration. You are titrating that borax with the HCl. So it is one kind of the basic compound. Okay. See how to prepare that borax. That borax can be prepared by means of colemanite. Means it's the name of that the mineral. What is the formula of that? Ca2B6O11. It is a general representation for colemanite. It reacts with a basic carbonate. That's a sodium carbonate. And after heating, you will get this borax. Its formula is Na2B4O7. Actually, water of hydration or crystallization remains 10H2O. Because of that crystallization that we get. Good crystals that we find because of the water of hydration. Okay. Plus a sodium borate we get, and the calcium carbonate. Your calcium carbonate they are showing as a precipitate. Means these reactions are undergone in aqueous medium. And this, so that's a borax soluble in water. Sodium borate soluble in water. But calcium carbonate is not soluble in water. Yes, anybody knows what's the other name of calcium carbonate? Where do you find this calcium carbonate? One material is there that is used for teaching purpose, and that material remains with that calcium carbonate. It is rich in calcium carbonate.
Chalk.
Exactly, chalk, that calcium carbonate. If you put the chalk powder in the water, it will not dissolve. Other calcium oxide, CaO, or quicklime that we say, that calcium oxide, if you add water in that, it forms calcium hydroxide. It's a clear solution. In that clear solution, if you pass carbon dioxide, CO2, then because of CO2, that clear solution becomes turbid, whitish. That whitishness because of the calcium carbonate. So quicklime will turn to white. So this calcium carbonate is not soluble in water. So therefore, downward arrow is represented. But other two compounds which are soluble in water. What's the second step? Whatever the filtrate is there, filtrate means clear solution. In that clear solution, pass carbon dioxide, excess of carbon dioxide. So what will we get? Sodium carbonate back, sodium carbonate return, and our desired product, that's a sodium, that's a borate, or you can say borax, that we can get, Na2B4O7. I repeat, colemanite when reacts with sodium carbonate in aqueous medium, and if you boil the solution, we will get precipitate of calcium carbonate, and if you filter that solution, we will find borax and sodium borate. That sodium borate, if we react with the carbon dioxide, we will get the borax. This borax in double way we can find out. And in addition to that, sodium carbonate. And the sodium carbonate is less soluble in water. It's soluble in water, but less soluble in water. And because of that, we can separate this sodium carbonate and we can get that borax. So this is the one method by which we can prepare or synthesize the borax. This is one method. Second method is from the boric acid. Boric acid when reacts with sodium carbonate, boric acid, though you are finding 3 hydrogens, but it is a weak acid. Because strength of acid doesn't depend on the number of hydrogens, it depends upon the ability of that compound to furnish hydrogens. The boric acid reacts with the sodium carbonate to form the borax, and water and CO2. CO2 gas will release out. Actually, in gaseous medium, CO2 is soluble in water. So partly it will go and partly it will dissolve. And afterwards, different ways are there by which we can remove the carbon dioxide, and we will get the sodium borate, or you can say it is what, the borax. The second method. First method by colemanite and second method by boric acid. These two methods, if you remember, sufficient. Okay. One thing I forgot: applications of diborane. I think I told you diborane. Yes, I told. Yes. Sorry. I repeated that. That's a rocket propellant and all that I discussed that part. Okay. So diborane and tetraborane, these two compounds we have discussed. Any question about that? Any doubt?
No doubt.
No.
Now I move to the next point. Chemistry of silicon and germanium, which included in your syllabus. And at the first, they have asked the concept about SiO2, silicon dioxide. Silicon dioxide is one of the important compound from industrial point of view, and is very stable, is very inert, and that is because of its bonding. One silicon can form 4 bonds, and oxygen can form 2 bonds. So one silicon oxygen double bond, other silicon oxygen double bond. Because of that, the strength is there in the bonding, and due to which it is considerably stable. It can withstand at very high temperature. Therefore, we say it is what, the inert compound or the stable compound. So the properties of silicon dioxide that you can study. Now digital clocks are there, but previously this silicon dioxide or silicates were widely used for the preparation of quartz. Quartz applications are there now also, but in watches, whichever the quartz were used, now those applications are decreased. So structure of silicon dioxide means a 3-dimensional cluster structure. If you want to see, it is likewise. So here silicon undergoing sp3 hybridization, and one silicon attaches to one oxygen, other silicon attaches to other oxygen. I said silicon oxygen double bond when it is heat, one entity. But when remains in a cluster, at that time, this silicon will attach to this oxygen. So this one silicon attaches to the 3 oxygens, and by the way, other silicon, so network can be established. Overall, if you see the 3-dimensional arrangement, total number of silicons will be half than that of the oxygen. Therefore, formula remains SiO2. in solid state chemistry, in structures of solids, you have studied NaCl. Why formula is NaCl? That one unit cell you have to study, and in that unit cell, number of cations and number of anions you have to find out, and accordingly formula decides. If you say the calcium fluoride, CaF2, so there one calcium in unit cell and two fluorides remain, and therefore formula remains in that way. So here unit cell point of view, simple aspect, the silicon and oxygen linkage is shown, but network kind of the arrangement is there, and because of that also it gets a considerable stability. So SiO2 linkage, so structure point of view, bond length, bond angles also are represented here. If you see, the oxygen in water forms the bond angle 104 degree. It is further relaxed, it is further increased, it is 144. But silicons are somewhat more rigid. The tetrahedral arrangement is what shown there. But bridged oxygens whichever are there, because of what some flexibility is achieved. So what exactly the situation is for that is bonding. So SiO2, its structure just I discussed, and then you can come to know its importance also. Other, we're talking about the silicon. SiO2 is one compound. Other compound of silicon is SiCl4, silicon tetrachloride. It has a wide application in preparation of polymers, silicones as a polymers. But how to prepare that? A simple method, a silicon, elemental silicon, if combines with chlorine, then we will get the SiCl4, a bit natural. Silicon being in the 14th group, it's like a carbon, so it will be tetravalent. So 4 wings, 4 orbitals, so the sp3 hybridized, it will spread, and along those orbitals, whoever chlorines are coming, chlorine 2p orbital or any orbital where at one unpaired electron is there that is approaching, you will find sigma bond, and SiCl4 can be obtained. Okay. That means for silicon, one compound SiO2 and second compound SiCl4. If you come towards the germanium, in germanium, how it occurs, how what is abundant, means its abundance, means earth crust. It is estimated about 7 parts per million, means ppm, that we are finding about the germanium. Important element from the industrial point of view. So how to extract that? So those things are what discussed. So next point, a silicon germanium is preferably how to get a pure germanium or pure silicon. So their zone melting method is used for purification of such materials. So what is that method actually? Here we are considering that zone, a polycrystal or the single crystal you can consider. See, polycrystal and single crystal, what's the difference? Single crystal means a growth one time only, a single crystal, and when many crystals do come together and then growth remains, that's a polycrystal growth. And by means of the zone refining, we can what? Purify that. So I show you that other diagram. This diagram is not so clear cut here. So zone refining, how it is used for the preparation. Just wait. It's okay. It's a single crystal growing. It is shown there. Here also zone refining is not there. Just wait. Okay. It's a float zone process. But basic I want to make clear. That's a zone refining. Just wait. Just wait. Okay. From this diagram, it will be somewhat more clear. I don't know how far you will pay attention towards this diagram. Yes. Could you read this diagram?
Yes, sir.
Yes, sir.
See, here it is shown now by yellow color. One circular heater is there. That heater likes a work like a zone. Means that region where yellow region is shown here, no? This region is molten. This region is heated. So strong electric arcs do remain present. They create a huge temperature, and because of that, elements get what? Molten. So how from one end we are moving toward the other end? How it occurs there? Zone refining process. Here in between we are here, but if you start from the end, then this portion will get heated, and after heating, the melting is possible. But we are not allowing to melt, means it allowed to fall down. So if suddenly whatever the little portion it melts over there, then whichever the impurities are there, the impurity may not remain at that proper position. They may change, they may get displaced. See, your arrow is shown there. Direction of travel of heater, molten zone, means from one end to other end we are moving. So impurity will go with the mobile phase, and germanium or silicon, whichever is there, it will remain there as it is. We're talking about silicon germanium element. Zone refining method especially used for germanium. And that molten germanium, whichever is there, that is going to shift from this one end to the other. And because of that shifting, melting, the impurity also will move. So impurity whichever was there, will move towards the other end. And this end, what will happen? Will be free from impurity, will be pure. And after some time, it will cool down, means it will be recrystallized. So recrystallized pure germanium we can get. And recrystallization is one method of purification. This year, if you conduct any experiment, then you will come to know that organic compounds, organic spotting, if you do, then you will recrystallize that solid, you will purify that solid. So recrystallization is one kind of purification. Why? Because what you are allowing, you are breaking that construction, what the crystals are obtained, and again newly formation. When new formations are there, then whichever the impurities are there, those will be eliminated. Means it is like how, just for the understanding point of view, if you consider one house, then first time when you consider, at that time chances are there, the errors are there while constructing that house, mistakes are there. But if you demolish that, again you reconstruct that, it's just for the understanding purpose, then those errors you will not follow, you will eliminate those. So when newly construction occurs, at that time which of the impurities mistakenly are trapped, now those impurities will move out through the mobile phase. So when melting we do, that's a zone refining, the zone purification. After melting or along with that liquid, the impurities will move. And that zone refining is only one way. We are not moving longer time. We are moving along that rod. We are moving along that metal. So zones, stepwise we are moving from one end to the other end. Along the direction of the heater, along the direction of the coil, the impurities will move. So what at last you will find, this one end is most pure and other end is impure. No problem. That impure end that we cannot remove, but at least we are getting what the other portion, which is what the perfectly pure. Means from industrial application point of view, purity matters. And for purification, that's a zone refining is used. So previously, what is zone floating refining was there in previous diagram, or one recrystallization is there. Just I showed to you now, recrystallization. Yes, zone float method. See, this is a zone float method. Means what is happening? You are finding heating here in between. But in true sense, what happened? That heating is started from upside. It started outside and it came in between now. And slowly, it is what coming down. And upper end we are getting what the more pure. It's just what the vertical arrangement is there. Yes, the Joukowski crystal puller means here we melt that and slowly we want to stir that, so that what happen, crystal formation occurs and we allow the crystal to grow. Very interesting portion it is. And that crystal, large crystal can be obtained and that remains for the more pure. So for that the arrangement is shown. A section is what taken and how that arrangement is there is represented. Here also heating is there. If I have to show this diagram again, the principle is same. That's a zone refining, melting is what important. Okay, just I show to you now. See here. Yes, could you able to read this diagram?
Yes, sir.
Or shall I magnify?
Yes, sir.
Okay. See here, the seed is shown. Seed. That's one needle-like portion there. That's a seed. So what is seed? I come to that point. But pay attention. Very interesting term it is. Here, single silicon crystal. Whatever you are finding on this large cylindrical is a one crystal. Sodium chloride crystal that you are finding is a large grown crystal. So single crystal growing is also one new technology, new method for the purification. When we study the material science, the concept we are the more clear. So this we want actually, but for that seeding is necessary. I'm coming to that seeding portion later on. See the next point here. Here quartz crucible is there. This portion of crucible. Crucible means time being understand it's a container. Container made of quartz. Quartz that we have studied is SiO2. Their quartz is used for industrial application. This quartz because it can withstand at the high temperature. We are doing heating there, and which will withstand at high temperature. Therefore, quartz material is used. And see here, outer jacket is there, and the jacket is with the water. Water cooled chamber means it is for cooling purpose, because for recrystallization after melting, the cooling also is necessary for cooling purpose. And here it is a heat shield, means inside there is a strong heating, so that should not affect our outer section, outer region, and therefore there is a shield or the protection. Here see yellow color that you are finding, it is a heater. It became angry, therefore yellow color is shown. It's a carbon heater. See here inside. The graphite crucible also shown, means graphite containers are there. Crucible means container. And here stand-like arrangement you are finding. The stand-like arrangement means it is support. It is a spill tray, means if anything comes out, then that extra things which we falls down, then that can be removed. For that purpose, the spill tray is there. And these are the electrodes. What is the carbon heater you are finding now? Those are related to the electrodes. Why? For or heating purpose. So overall, this diagram is like a cylinder. One drum is there, and in that drum, heating is going on. As like the roasted cashew, drum roasted cashew we find. So in drum we throw that the cashew. Likewise here, these are not freely movable. That silicon is in a container. So whatever you are finding now, here one tub is there or one crucible is there, one container is there, and that container is made up of what? Cords. And addition to that support, in addition to cords, there is a graphite crucible also. See, inside there is what? The quartz crucible, and outside there is what? The graphite crucible. So quartz can transfer the heat, but it can withstand at what? The high temperature. And graphite is used for the communication of the heat or to transfer the heat. So it is a container, and in this container, this yellow or red color you are finding now, that is our element which we want to purify, that is silicon. And from this silicon, impure silicon, we are getting pure silicon, and pure silicon we are withdrawing in terms of one crystal. That crystal will what? Grow. That is shown as only one crystal will grow. Okay, for that I give you one example. If you take ice and if you melt ice, means you will get, ice means also water, melting water, but I say the solid water and the liquid water. What are the liquid water you get? Can you find the solid water from liquid water? Can you get ice from the water? See, ice melts, you will get the liquid water. My question is, can you reverse that process? From water, can you obtain ice? Can you solidify that?
Yes.
How?
By freezing.
By freezing, by cooling. Yes. If you cool the molten thing, means the molten silicon, we are cooling. And while cooling, a solid will form. But while formation of solid, means it's a slowly we are decreasing. As slowly we decrease the temperature, slowly crystal will build. Crystal growth remains the slow, and accordingly size of the crystal remains. One interesting example I give it to you. If you go to the Shiroda, at Shiroda region, a salt is prepared, common salt, and in market branded salt you get. There remains a difference in color, I agree. But one more remarkable difference remains in that traditionally obtained salt and branded salt. What is that remarkable difference? Yes, students, are you getting my question? No, if no, then say no, then I'll repeat the question. Okay, then be clear cut in your communication. Why are you wasting time? I repeat, Vasant, see, it's a good thing you did now. Likewise, I expect from others. Now 17 students are present, but only one student has replied. Pay attention. Traditionally, how salt is prepared? We block the water of the ocean or the sea, and we allow the water to evaporate. After evaporation, we get a salt. Therefore, I give an example of Shiroda, where you can find the salt belts are there. Salt preparation remains in progress. Not now in the rainy season. It remains in what? The summer season or winter season. It is a traditional salt. And other salt that we bring from the market, color difference remains. In addition to the color difference, what is the significant difference in those salts? Traditional salt and market salt or branded salt. Yes, is my question clear?
Yes, sir.
Okay, Shubham replied. What about others? Mandar replied.
Yes, sir.
Prathamesh replied, Saurabh replied, Bhakti replied, Chirag replied, Vasant replied. Okay. Now I want answer. Yes, Joynita, Gauraj, Gitanjali, Jailina. Yes, all are answering. If you compare, no, then just compare those salt, traditional salt and branded salt. What difference you find? Are they completely same, perfectly same?
No.
Then what's the difference, Saurabh? About their physical nature, about their appearance, tell me, only appearance. Chemical difference, I am not asking. I am asking physical difference, appearance difference. Yes, Mandar, absolutely. Size difference. Which salt is larger? Which crystals are larger? Crystal growth is more traditional or branded? Exactly, Shilpa, Saurabh, Bhakti, right. Traditional salt is larger. Why it is? Because seawater, when we block in one plot and we allow the water to evaporate because of the heat, water will evaporate. Water only will go. H2 will go. But other contaminants, other dissolvents, the salts which are present in seawater, those will remain there only. So previously, those salts were in large amount of water. After evaporation, water remains less. So there remains a saturation. Solution which was unsaturated, last year syllabus, unsaturated means complete dissolution. Now it becomes saturated. After supersaturated, supersaturated means a solubility is less. So water is less, but salt is more. So slowly water goes out. slowly salt forms. When salt forms, at that time, one salt interacts, one salt means one crystal or the one formulation interacts with neighbor. That interacts with neighbor. That interacts with neighbor. Likewise, large community of neighbor remains, and ultimately crystal remains large because slow evaporation, slowly you are allowing to grow. Our concept, is it crystal clear that we say no? Okay, slowly we understand, slowly we digest, and at last that concept becomes solid. Concept becomes big, concept becomes understandable. So the crystal clear means clarity remains proper. So it is a readily notable crystal you can find. But suppose evaporation remains fast, means if you take a salt solution and you evaporate it on the burner in kitchen or in the chemist laboratory, then the fast evaporation is there. Because of fast evaporation, the crystal growth decreases. Crystal growth affects small crystals you will find in the branded salt, while in traditional salt you are getting large crystal. My point of interest here is to inform you crystal growth depends upon the cooling or the evaporation of the solvent. Here there is no solution. Here pure element is there and little impurities are there. What we are doing? We are molting that. We are heating that. So molten silicon, and from that we want silicon. So we have to cool that. So after cooling, we will get slow cooling. But by the way, sometimes seeding is necessary. Seeding is necessary. For example, when I ask question, then which salt will be larger in size, which crystal larger, traditional or branded? Then Mandar has answered. Mandar is a seed. Mandar is a one initiative. Once he has taken initiative, others are answering. Is my question clear? Then one answers yes, then others do follow. But if one do not answer first, then everybody wants, let some other body answer, let some other body answer. But one time incident occurs, one time initiation takes place, then others can support. But somebody should be there, somebody initiation should be there, and that initiation is done by this needle-like situation, or needle-like, you can say, or wire. It is a silicon. It's a pure silicon already present. Just touch that silicon, so that silicon will come to know molten silicon. Yes, it's my form. I can go in that form. So newly forming silicon who are interested to become a solid, they form other solid and they link to that. And that linkage remains in continuation and the chain increases. Means it is a very horrible situation. Means at Afghanistan, what happened? If somebody went there on the aeroplane, because inside there was no space, not allowed. So one catch aeroplane, he worked as a seeding point. So other also felt, I also should do that. So that momentum or the continues. So in our behavior, how it happens, likewise, here also, if somewhere they find the opportunity, they find the way, other will what the follow that. Many times I ask the question, no? So one initiates, then after we follow, and many do what follow. To get first answer, we get time. Students, are you following what I'm saying?
Yes, sir.
Yes, sir.
Yeah. So by means of this seed, the initiation occurs, and then crystal grows, and that crystal will be the pure crystal. That's a purification of silicon. And for that, we use this crucible. Crucible is made up of quartz, and below that support there is of the graphite. And for heating purpose, the graphite electrodes are there, or any other electrodes we can use heating purpose. But in order not to come out that heat outside, the jacket is there, coating is there, cover is there, and for further cooling purpose, the water is there, simply blue color is shown there. So this PDF file I had given to you, you can go through that and you will understand the purification of silicon. Yes. Now what we have learned today as an assignment: first point, applications of diborane. Second point, tetraborane, its structure. Third point, we discuss borax, preparation of the borax. Fourth point, silicon and its compound. That's a silicon, SiO2 as one compound. Fifth point, SiCl4. Sixth point, germanium. Occurrence is given there. You can prepare the notes of that. And 7 point, purification. And for purification, zone refining as one method. Floating zone refining, second method. And Joukowski, this method now. That's a crystal puller, one crystal growth method. So all these methods of purification that you have to study. So prepare notes, So more time is necessary for that. So instead of asking at what very next Saturday, I will give sufficient time to you. And after 15 days, or maybe now Ganesh festival is at 10. So take your 7 days, say up to 17th or say 20th of September maximum. I want these notes. Is assignment clear?
Yes, sir.
Yes.
Yes,
So
sir.
all things I had not discussed in detail. Study material is given to you. You have to work for that. When you work, you will be the questions, and for the questions, I am here to answer. Okay. Let us discuss in what the next lecture. Shall we stop now?
Yes, sir.
Yes, sir.
Yes, very good. I stop the recording and I declare here today's session is over. Attendance, those who are present regularly, they can give that regular attendance, and those who are going through video also, they can give the both. And those who are absent, they can give only attendance of the video lecture. Video of today's session, I will upload by night. Yes, quit now. Lecture is over.